Okay, hello everyone. We are doing a working session here talking about multicomputation and its relationship to Wolfram language. So let's start off with Nick talking about pattern matching experiments. So as I understand this, these are functions that dive into the innards of pattern matching, basically.
Well, not really. They're completely separate system. They're just re-implementing all the pattern primitives.
Do they do it buglessly? I mean, do you know, have you run the tests, the pattern matcher tests on them and things?
Well, some of them, but I just have a plan to again re-implement it from scratch. It's a little bit different, in a different way. Because I realized I need some laziness for it to work how I want it to.
Okay, but so let's understand what this is. And I'm surprised if we're talking about this kind of language design that we don't have Christopher and folks like that here. Maybe I mean, if we're going to talk about this, could we please ping Christopher?
Yeah, I'm pinging right now.
Okay, but Nick, can you explain the purpose of these functions, which I think I understand, but can you try to explain that again?
Well, the purpose is, the first purpose is just for me to understand how patterns work. That's the first goal. And the second goal is just to make it a little bit more informative. Each pattern matching procedure in the language comes with additional information what actually happens with some kind of intermediate object.
Right.
Which I call pattern substitution.
Okay, but so the question here is, so there should be a flow in which replace, for example, becomes a two-step process where first it finds the bindings and then it applies them. Is that correct?
Well, yeah, even a little bit more than that, not just bindings. Just having procedure just that finds bindings, that was my first implementation, but it's not enough because this intermediate object have to have more information than just symbol bindings.
Yeah, right. It has to know which part of the expression was matched to this. Is that correct?
Yeah, basically each pattern. You have a pattern and you know position of each pattern object there. And you know, even if this even if it doesn't consist any symbol there that you want to bind it into, you still want to know what is this pattern binds to.
Like blank blank, that it bound to 137 or something.
Yeah, exactly. Yeah.
Okay. And do you deal with orderless functions and things like that? Flat and orderless functions?
I've tried to get that flat orderless one identity attributes to work too.
Is there an obvious reason why you don't try and put this into I mean, in other words, if you were looking at the internal code, maybe the internal code is already doing a bunch of this stuff, and it's just a question of using those internal functions in an appropriate way. Have you considered that possibility?
Well, I've looked at it slightly already. It doesn't look like it's doing something like that. There's some idea of matchboxes that I think.
Oh gosh, those were mine. That's from 1987.
Yeah.
1986. Yeah, okay. I think that was almost a pun, this idea of a matchbox, but yeah, go ahead.
Basically, I don't know yet how it works, but I think it's doing it much more complicated way than I wanted to do it.
Fair enough. But if you can do it in a way that is, correct, that's quite interesting. I mean, it's quite interesting for other purposes like the compiler and so on, I would think. Because if your thing is top-level code that does this, it's not obvious it couldn't do it on expastructs, for example.
Sure. Yeah. It can work in both on any expression.
Right, but the expastruct is the internal representation. So in other words, if your code ran on the expr struct, my understanding is if your code could be compiled, we would have a compiled version of the pattern matcher.
Yeah, maybe. Well, it doesn't have to be an expert struct. So because it's like I'm trying to take a good care of actually what expression evaluates and what not. It's like right now I just have a bunch of unevaluated holdover arguments in appropriate places.
Okay. Okay.
And I don't format it necessarily.
Okay. But so there are really two, this is a dual use thing because it's really something where it's both relevant for us to sort of see how to do, well, you're going to talk about multi-evaluate in a moment, but this is what you have here, if I understand correctly, is the raw material that would be needed to take pattern matching multi. Is that correct?
Well, that would certainly help, yeah. I already said that the multi is just replace list. But this is just replace list with more information.
Yeah. Right, but I mean, this allows one to, for example, get causal graphs and things like that, whereas pure replace list does not.
Yeah, and probably have a way to traverse the matching, the pattern matcher differently with different traversal orders.
That's a good point too. And the other thing it will allow is theorem proving stuff, because it will allow, you will have the trace of what sequence of pattern matchings actually took place to get from X to Y, correct?
Yeah. Yep.
So I mean, the representation that you have of the matching and replacement process should be compared to the representation that find equational proof generates.
Well, yeah, basically, yes, it is the same thing. It's just proof is also have bindings that go in both directions, so it's a little bit more general than that. Right now, pattern matcher is only single directional pattern matcher.
Mm-hmm.
So the generalization would be to make it bidirectional, and that would correspond to a proof.
Why is it necessary? Why don't you just take every rule and replace it and make two copies of it?
What do you mean?
Well, to make it bidirectional, just have A goes to B and B goes to A, both be rules in the collection of rules.
No, by bidirectional, I mean that right now I pattern match patterns against expressions. But in bidirectional, I want to pattern match patterns against patterns. So if I have a pattern object, like alternatives in the expression, I want to match it against like in different direction.
Okay, fine. So that is the two-way rule type.
It's not quite two-way rule. Two-way rule is just two rules separately. But when you have like just a pattern and another pattern, and you want a pattern matching in both ways, like find a unification, most general unifier, or whatever you want to call it. This is a bidirectional matching.
Right. But I mean, right now, even, I mean, notationally, we've got this idea, you can write X blank, I don't know, X blank, Y, whatever, two-way rule, Y blank, blank, X blank or something. Is that correct? That's a meaningful thing to write.
Well, I'm not sure about that.
I mean, what I'm saying is, go ahead.
You have blank on one side, double blank.
All right, forget the double blank. Forget my double blanks. Okay, forget my double blanks.
Okay.
Okay, so I mean, then the basic point is that we're used to the idea. Okay, so we've got several things that need to plug into this. For example, find equational proof does not accept things in this form, does it?
Yeah, in exactly this form now, but it's equivalent form.
I know it's an equivalent form, but I mean, even to convert, even having conversion functions between f of x, y, equals f of yx. And the pattern form of that seems like it will be a useful thing to have.
Yeah, maybe with an explicit quantifier, like for all in this case.
Yeah, right, fine. I think that seems useful to be able to convert between the pattern form and the algebraic form. Seems sensible. I mean, and then what you have here is, let me just see so let's see, pattern substitutions, what does that do?
Well, that will produce this giant unformatted currently object.
My God. Can I make that pretty printed slightly? What can I do to make it
Well,
slightly?
if you get Wolfram patterns right now, that would will get rid of this context. Backtick. Wolfram backtick patterns backtick. Just get this context.
Okay.
So this like the outer head is a sum. So it means like every element in that sum is a separate thing that can be matched. So like if you want just a single match, you can just take the first one and ignore all the rest. And if it's the product, you have to match all of them, all the elements of a product.
Yep.
And if it's a part substitution, it's something like a hierarchical structure that contains an actual part and a potential sub-pattern. So we can recover the information.
Okay. See, where am I putting this? It's research, multi-computation. Kristen, where am I putting this? SW
Put it in,
note?
yes. Yeah.
Okay, so this is a representation of what this you could derive from this the multi-match for this. Is that correct? By multi-match, I mean all possible matchings.
Yeah, like bindings. That's why you separate function that just applies to this object and gets all the bindings.
Mm-hmm.
And
go ahead.
And in general, this object could be lazy. That's what I'm gonna do next. So right now, it's just I have a third argument to pattern substitutions, and it will try to make to do it efficiently and to extract just as many as you want. But I think it shouldn't have this argument. It just be lazy generator that I can just traverse however I want.
Right. Okay, but how do you access that to say what traversal you want?
Well, there's a natural traversal. It's like someone wants to go like breadth first, and product is the other way around. It's similar to just like if you have a polynomial, if you have x plus y times a plus b, and you want to expand it. It's what would be the order of your individual terms? This is analogous to that. You have a sum and a product, and you want to expand it and just take some number of terms from the expansion.
Right. Which would correspond to a particular choice of bindings. Is that correct?
Yeah, each individual is a particular choice of bindings.
Right. Each term in the sum is a possible binding that has whose product elements, the elements of the product, the monomial, so to speak, correspond to the particular bindings of particular variables. Is that correct?
Yeah, if it's already in expanded form that you have just sum of products, then yeah. But product also can contain a sum, and this sum can contain a product.
I get it. So I mean, it really is, as you say, much like polynomials.
Yeah.
And so I mean, essentially, this is an algebra, a matching algebra. So how do we think about, I mean, I see. So is there a graphical representation of this matching algebra?
Hmm.
I mean, sum is like parallel paths. Somehow. Product is not really sequential. Okay,
it is kind of like a tree.
with subtrees for the inner sums.
Yeah.
That parallelizes, that each sum parallelizes, each product is sort of sequentially going down. Is that right? So that as you traverse, your ultimate match is kind of the leaves, is the paths through this tree. Is that correct?
Yeah. The matching should find the leaves, and I have substitution values as my leaf expression. That just holds the actual parts of an expression that you're matching against.
Well, maybe you could try drawing those trees. It might be illuminating, and that tree will in turn have some relationship to the expression tree, won't it? I mean, it's some kind of. Am I making sense?
Well, I don't know. I don't know what is this. I don't think there is a relation to the expression tree, the immediate one.
Okay, but anyway, so then, all right. So there's a representation of the matching algebra, and from the matching algebra, you can extract certain things like a particular set of substitution bindings for a particular path, a particular sort of, monomial, effectively in the matching polynomial. Correct?
Right. Yeah. So it would be like the simplest example would be substitution bindings already have like a third argument how many you want to extract it. But so if it were a generator, it would actually traverse it efficiently and just extract as much as only the ones that you want. The first
right.
one you want.
But this is the full multi-way version of substitution bindings. This is generating all of them.
Yeah.
Correct?
Yeah.
Okay. So in a sense, just like we have that evaluation graph, let's see, I mean, the thing we're talking about over here is a matching graph. And then, then there's also a multi-way matching graph. I mean, I'm
Maybe
confused.
it's a tree. I'm not sure why it's a graph.
Okay, but I bet this is a graph because there are lots of shared pieces there, I think. Well, okay, but in any case, so the thing that you're going to be able to do from this. Okay, my question would be the proof function from find equational proof. What's the relationship of that to what you have here?
So the proof function takes in a bunch of lemmas and just it runs them on your initial axioms and try to come up with the hypothesis. So I'm not sure. It's not there is no immediate connection again.
Well, okay, but look, what you do when you're, a proof is a sequence of rule applications where you know where they're getting applied. Is that a fair characterization?
Yeah. In this sense, yeah, this is also kind of a bunch of instructions. I have like in a separate function here in the Packlet called substitution apply. It's if you feed this object that is returned by pattern substitution and the pattern that you generated it from. The goal is that it should recover the expression back.
Okay, which to me sounds awfully like proof function.
Yeah.
In other words, well, you've got a set of replacements, and you're claiming that, given those replacements, you will recover this tautology, basically.
Yeah, you just replace all the pattern primitives with some expression, and your goal is to recover the expression back.
Yeah. Okay. Well, so the next steps for this, what are the next steps for this section here?
The next step is to make it lazy generators. And I'm like kind of marinating that idea still. I also reviewing my lazy Packlet, and the polls that we have at summer school also related.
The which? Sorry, which? At some school? What?
I think some student, I think it was Athena, who made
Okay.
some const list and const tree structures, data structure.
You should be in touch with her. I think she's interested in exploring this further.
Yeah.
I
basically got the same kind of idea with const list and const tree. It even has the same name.
Oh, really? Okay.
Yeah.
Okay. We good to make contact with her about that. Maybe Kristen could make sure that happens.
Yeah, I'll make sure that happens and connect you.
There. Okay. So, all right. So I'm still trying to understand. So the suite of functions that we're going to have here is basically, it is the more atomized version of pattern matching. So it is pattern substitutions. It is this matching algebra type thing. And then it is processors of this matching algebra. Is that correct? And then there is also a need to essentially foliate, traversal order, whatever you call it, the expressions in the matching algebra. Is that correct? So you decide which match you actually want to use.
Yeah. If that like pattern substitution would return some kind of lazy tree, then you're just gonna be a way to feed it a traversal order that we already have different notions of those, and recover the like individual matchings.
Right. Now we don't have lazy trees, do we? I mean, you need to build a lazy tree.
Yeah.
Okay.
Lists and the trees are essential data structures that should be there, which was the
Right.
project by Athena, and I also have the same implementation.
Okay, so there's a separate. Okay, so lazy structures. So I think in our language that will be called delayed list or something.
Oh, I don't
Set
necessarily
delayed.
like it. Delayed. Maybe it's like hold lists, because it's essentially just some new head with hold all or hold the rest.
Held list maybe. Or delayed. Okay, but so, or even list delayed. I don't know, since we have set delayed. Not that anybody knows it's called that, but that's what colon equals is.
Yeah, rule delayed.
Yeah, right. I mean, list delayed seems like not completely stupid as a possible name. But so then you've got also the notion of a tree delayed.
Yeah, but
And
essentially uses the list delayed as its children, kind of.
Okay, so list delayed supports certain kinds of accessors, like part numbers and parts and so on. Is that correct?
Yeah, you have to like the whole purpose of the whole difficulty in the whole implementation of this list delayed thing is just coming up with the app values that work with it for different list functions, like partitions, especially, and make it parallel. Partition and parallel map for the lazy lists also the most tricky, I think. That's it.
Cool. Well, anyway, so So, Ethan on a live stream is asking about compilability of list delayed, which is again an interesting question. But okay, so you are basically backing into implementing things like list delayed. And that's a data structure that you want to use for this matching tree.
Yeah.
Which then still has these primitives in it that represent sort of granular components of the matching process, like substitution sum and substitution product. I mean, I'm just, the thing that's driving me crazy about this is they are so similar to type sum and type product.
Oh, yeah, it's the same kind of category. You have products and co-products.
Mm-hmm. I mean, okay. But then, okay, given a tree delayed, then there would be something like tree map with a certain traversal order. Tree traversal order error blah. And that would give us, and one of those is the traditional, okay, question. How do we get, and this is a tree question for Ian, how do we get the first element in a certain traversal order out of a tree?
So you could list all of the subtrees in a given order, but we
Okay.
don't have
Kind of inefficient. So
lazy part extraction.
So how would what would be the way of doing that? Listing the subtrees in a certain traversal order?
Tree level of the tree, comma, all, comma, tree traversal order, whatever.
Okay, how do I get the first? How do I get the, what's that?
Just take part one of that list.
Yeah, but I don't understand. I just want to get the visit order. No, I want, what do I want to get? I want to get the first element that I get. I guess I want to get the first leaf. That will be the thing for Nick. The first leaf with that traversal order.
Maybe a path from a root node to the leaf.
Yes, okay. How would I get that here? Seems like there needs to be another utility for trees. Maybe this is something Nick could build. Okay. So
I'm not sure what you're asking for. Like you want
the path
first leaf in that list.
I want 286. Because why do I want that? I want that because that's what our pattern matcher actually does. See what I'm saying? It's taking the first match in a depth first traversal of the match tree. That's correct, right, Nick? It's the first match in the depth first traversal of the match tree.
Yeah, it should be, yeah. So like 286 is like a product or just a match in a sequence.
Right. Okay, well, look, it seems to me there are things you could do where you can actually make this explicitly as a tree, and then we can maybe understand a little better. Okay, let's move on, unless you want to say more about this section. We're going to run out of time. So I want to...
I have questions about this section. How are there more than one bindings for shortest? Shouldn't there be a unique match?
There's
Well,
double... Go ahead.
How can I define it? Because it's a replace list, basically. The difference where you put the shortest just defines how they're ordered. So it's like the difference between first and second shortest is only the order of those bindings.
That's an interesting claim. I mean, that shortest is not pruning the tree. That's what you're saying here. Shortest is merely reordering and not pruning the tree. Whereas Ian is saying, why isn't it pruning the tree?
Well, if it were a lazy tree, it just would decide how I would traverse it.
Well, but I mean, the fact that
the shortest sequence that matches blank should just be a single element. I don't see how shortest could match a sequence of two or more things in this case.
no, I mean, without a slash semi or something like that, that's annotating this, all of these matches could never be realized. Correct, Nick?
Yeah, if you just ask for first one, they shouldn't be even considered.
I know, but what Ian is saying is, given the semantics of shortest, okay, so I don't know whether replace list, I mean, we can clearly determine that. If we say, you know, replace list, oh ho ho, I had no idea. Well, you're right, Nick. Ian, does that surprise you? It surprises me.
Yeah, I don't understand that.
Nor do I. I mean, it's a different semantics from shortest than the one I thought it was using, and I think we need to dive into this to understand that. But that's okay. Okay, is this what we were looking at already last time?
I think, yeah. Yeah.
Okay, but where did we want to go with this? This is, I mean, this is the multi-way trace graph, correct? That we have here.
Yeah.
What's the relationship? Okay. And so then, I mean just
so
like
this is using trace graph. This is using trace graph to visualize the things that actually call the evaluator.
Mhm.
Everything else is like replace list with rules.
Yeah, well, the issue is, as we show the breakdown of how a computation happens, how broken down do we want to go?
I personally would like just some very interactive thing that you can just just select what piece of part of your expression you want to evaluate and move this graph, not generate it like from scratch with all possible directions. Actually choose.
Mm-hmm.
Just an interactive evaluator.
Well, see if you can build something. I mean, I think that's one thing I think that'd be really good, but I think another thing is understanding the multi-way version, because, you know, one of the big purposes here is to see how to make, you know, again, I'm looking for things like find replace path. You know, how does that get represented? You know, we've got this fully, you know, everything multi-way thing, and then we've got, you know, find replace path that is just finding particular paths in here. Am I right? Or actually, find replace path is finding paths in this thing over here, which is not the evaluator, but rather the substitutor. Correct?
And yeah.
Did you build something? Is this Trace Interactive something you built?
No, it's not mine. It's by Richard. It's an old thing already.
Okay.
But something like this that where I can also pick the like different parts and different results if it's a like replace list ambiguity, basically.
Gosh, I've never used this. This is cool. Yeah, I mean, I think this is cool, but I think it needs more, you know, it needs more of a map showing you where you are in the whole graph, I think.
Right.
Oh no.
There's a system function trace dialog
Oh, that's
which
right.
this may be using. I'm not sure.
But look, how do I get out of this? Help! Anybody have any idea how to get out of this? Okay.
Shouldn't have closed this notebook until it finished.
Thank you. Yes. I noticed that now. Oh gosh, I realized I was running some big jobs overnight. I hope this doesn't help. Anybody got any idea? Maybe somebody could ask Rick Hannigan how you get out of this. If Kristen could message him.
Yeah, I messaged him right now.
Okay. Okay, so Nick, are we these things here? Which of these are? Is this from my notes? Kristen? Yeah, okay. All right. So can you come up with your version of this? Because I don't think you agree with quite all of these functions, right?
Well, some of them are just unrelated to the thing I've done. The most related is that detailed replace, I think.
Okay.
And find pattern rules.
Okay. Okay, but the thing we need to do here is we've got certain things like we know we want to have, conversions between these forms. We know, I mean, let's just try and start making something that's a production type thing that is at the very least, I mean, even things like your, applying by substitution, things like that. We need to have those functions, right?
I also think it's a really multi-replace thing that does it.
Okay, fine, but what we're trying to do is get those to the point where they can actually be built-in functions.
Yeah. Yeah, that's tricky. Yeah.
Which means all of those things have to fit together. And our goal in the larger scale is, as we have other applications of multi-computation, and as we want different kinds of observers and things like this, just like the good news was in doing the mathematics project, we could pretty much leverage existing token event graph and nest graph tagged and so on things for that project. We didn't have to build custom new multi-computational functions mostly. At least that's my recollection of it. The goal is, and again, one of our output goals is multi-way graph needs to be replaced by cleaner, better, built-inable functions, so to speak. Does that make sense?
Wait, do you mean multi-way system?
That's what I mean. Multi-way system.
Okay.
It's probably renamed multi-way graph.
It's more not a rebuilding of it, but like completely thinking how to make it more concise.
Yes.
Just divide it into more approachable elements. Like we don't have to have so many properties of it.
Exactly. We can have. We make
right
a.
now.
Go ahead.
Right now, I just have a multi graphs, just states graph with tags. It's like the whole output of a multi-way system for any kind of system that I want. It's just some kind of version of a nest graph with very convenient tags that I can use for extracting causal information.
Exactly. That's what we want to have. And then we'll have a function, branchial graphs or something, that goes from that and finds, and gets that piece and so on. I think the goal should be, that, the goal is for 13.2 to see what we can do to actually put multi-computation functions into the language. Because I think we're stable enough on a bunch of these things that we can start to do that. Now, I think that as we try and merge essentially the quantum gravity story, the spatial information with the branchial information, that's where things like local multi-way systems and all those kinds of things come in. And that is more complicated. But I think we need to try and see how we are doing the existing stuff, in a way that can actually fit into the language, and that's, I think, what we should aim for.
Well, how about just we update NSGraph to be essentially a NSGraph tagged with some
Yes, I
nice
think that would be useful. Yeah.
and then update like all kind of system functions like cell automata, substitution system, Turing machine things. Instead of just applying to a state and get a final state, it also has some additional information of causality. I think that would be enough. And if you use this kind of function with this NSGraph tag, and it will tag with this additional information, you can extract causal graphs from it.
Why don't you see if you can figure out that design? Okay.
All right.
And remember, with NestGraph, when we talked about that last time, right, and hopefully there are notes from that, we talked about all these things about traversal orders and termination conditions and so on, right? Because that's what we need for this. Make sense?
Yeah.
Well, I mean, that's what we need. It's kind of complicated. And I think that's going to require, this is a complicated piece of design, right? And it's going to require a whole bunch more design meetings to straighten it out. But I think, the more you can build prototypes of these things or proposed final versions, the better, so that we actually start homing in on what does it really look like.
First, I need to figure out patterns.
Yeah.
Not everything at once. Okay.
Yeah, I understand. But I think we have to just make sure we know the path here that gets us to things like find replace path and all those kinds of things. Because that's, what we're getting is you're figuring out patterns. You've got this matching algebra. You've got that gives us the patterns have a certain multi-wayness to them. And yeah, I think that's what we're doing here. All right, we should probably wrap up for now here. So to be continued. Anybody, anything else for last comments here? Oh, okay. See you all soon. Bye.